Going to be talking about non-local games, compression theorems, and the arithmetical hierarchy. This is joint work with Hamoon Mousavi and Henry Yuen. So what are non-local games? These are games played between two players, Alice and Bob, and a verifier. Once the game starts, the Alice and Bob cannot communicate with each other, but they can agree upon a strategy beforehand to try to maximize the probability that they win this game against the verifier. And in certain strategies, we allow Alice and Bob to also be correlated quantumly, namely share quantum entanglement. What we really care about here is the so-called value of a game under some class of allowed strategies, which is just the supremum over all the winning probabilities over all the possible strategies in that class that Alice and Bob are allowed to use. And a game is defined via the question and answer sets that the question and answers can come from, a probability distribution over the questions, and a decision predicate that the verifier computes to decide if a given round of the game has been won by the players. The three main classes of strategies that are usually studied are the classical ones, namely when there's no quantum entanglement between the players, the finite dimensional quantum or tensor product quantum ones, where it models the situation where Alice and Bob use finite dimensions of entanglement, and the commuting operator model, which captures a situation where Alice and Bob share an infinite amount of entanglement. These three set of classes are separate from each other. These inclusions are strict since there exist games that have better winning probabilities when you use quantum strategies rather than classical ones, namely the CHSH game, and the MIP star equals RE result of G, Natarajan, Vidicrite, and Yuen shows that there exists games where you can win strictly better in the commuting operator in the infinite dimensional setting than if Alice and Bob have to only use finite dimensional strategies. Now that we know what non-local games and values are, there are four important computational decision problems associated to values of games that we can ask, namely the approximate and exact quantum and commuting operator value problems. And the exact quantum and commuting operator value problems ask what is the hardness of this following problem. If I'm given a non-local game G, how hard is it to decide if the quantum or commuting operator value of that game is exactly 1? The approximate version of this game is the promise problem, where I'm given a non-local game that either has a quantum or commuting operator value of exactly 1, or at most a half, and I have to decide between these two situations. And the first of these was solved back in 2016 by William Slofstra, where he showed that the exact commuting operator value problem is equivalent to the non-halting problem, namely that the exact commuting operator problem is co-RE complete. Later, Magina, Tarjan, Vidicrite, and Yuen in 2020 showed that the approximate quantum problem is equivalent to the halting problem. In this work, we resolve a third of these problems, namely we show that the exact quantum value problem is equivalent to the universal halting problem, showing that the exact quantum problem is so-called Pi2 complete. Pi2 being a class of languages that lies in the second level of the arithmetical hierarchy and which is strictly harder than the halting problem and non-halting. In this paper, we also give an alternate proof of William Slofstra's result using techniques that are more in line with the ones used in the MIP star equals RE paper. What remains is to characterize the approximate commuting operator problem, which is believed to be also equivalent to not halting, but that is an open problem. So this is again the complexity landscape of these problems associated to the values of non-local games. To recap, halting problem is the problem where we're giving a Turing machine M and an input X, and we want to decide if that Turing machine run on that input halts. Non-halting is the converse of that problem, and universal halting asks if I'm given a Turing machine, does it halt on every single possible input that it may be run on? The main idea, the main ingredient that we use for our result is something called non-local game compression. Compression was originally introduced by G and later developed by Fitzsimmons et al. And was the crucial component of G nut Vidic and Wright and Yuen's result that MIP star equals to RE. So a compression theorem allows us to take a non-local game and reduce it to another non-local game where the values of these games are related to each other. Namely, if the original game was perfectly winnable using a quantum strategy, then so too should the outputted game. But in a sense, it's compressed. Namely, the set of questions and answers that are involved in the game are reduced in size, and the complexity for the verifier to decide the decision predicate, namely to decide if Alice and Bob won a single round of the game, is going to be much more efficient in this outputted game, hence the name compression. So in particular, if we have a uniform family of games Gn, this compression will take the description of these and output the description of a new uniform family of games Gn prime, where if the original question set and answer sets for the games had size 2 to the n, the new question and answer sets for these new games will be exponentially smaller, and so too the verifier complexity will be reduced for deciding the decision predicate. Again, we want that the either quantum or commuting operator values of these new games to be very much related to the original games. And in order for this compression to happen, usually the idea is to delegate a lot of the verifier's computation to the players, and this involves forcing the players to share more entanglement. And we can usually, in these compression theorems, say something about how much entanglement these new games must have in terms of the original game's entanglement requirement. And depending on the exact relation that the compressed games and the original games have, we get different compression results for different applications. In particular, for our paper, we give a compression theorem that is very different from the other compression results that have been seen before, namely because it works not only for the finite dimensional quantum value of a game, but we can prove that the compression procedure preserves also the commuting operator value of games. So let's look at exactly what our compression says. It says that if we're given a family of games, it outputs a family of games such that we can lower bound each of the compressed games' quantum value as such, and also that if the original games in the family had a value less than 1, then the compressed games also will have a value less than 1. Putting these together, we of course see that the quantum value of these compressed games from our compression result will have a value 1 if and only if the original games had a value 1. So too, our compression guarantees that in a similar way, the commuting operator value is preserved. And finally, the amount of entanglement that's required to win the nth compressed game perfectly is lower bounded by the maximum of the entanglement that was required to win the original games perfectly and n. So these are the guarantees that we get from the compression theorem that we prove in our result. Now, in order to apply this to obtain our hardness results, we first prove something called supercompression. Now, in compression, we take a family of games, a uniform family of games, and produce a new family of games where the individual games in this new compressed family are exponentially more efficient than the original. Similarly, supercompression takes a uniform family of games, but instead produces a single game, where this single game will have a value 1 if and only if every single game in the original family had a value of 1, hence the name supercompression. Now we will see how we can use this compression result from our paper to produce supercompression. So to do supercompression, we begin with a uniform family of games. We define a new family of games Gn that use our compression result in their definition, and then we show that any, in particular the first game of this family, has the property that its quantum and commuting operator values are 1 if and only if every single game in the original family had this property. Furthermore, we will show that in the supercompression procedure, the outputted game will always have an entanglement requirement for winning it perfectly that's infinite. Namely, no finite dimensional strategy, individual one, can ever perfectly win the game, even though supremum over finite dimensional strategies may achieve this value. And then we will show how supercompression can immediately be used to obtain our results. But let's now go on and use compression to develop this. So let us define the game family from which we will select a game for supercompression. So let's explicitly define the verifier, what the verifier in the nth game in this new game family does. So the first step is that we feed the description of the verifier for these family of games to the compression algorithm that we produce in our paper to get the description of its own compression. Then with probability 1/2, we play the nth game from the family we wish to supercompress, and with probability 1/2, otherwise we play the n+1th compressed version of itself. Very importantly, this is not a recursive definition, since these compressed games are just another class of games. They do not call back to the original game. All we have is that their values are predictably related to the original family. And just as a sanity check, let's make sure that these family of games are in fact a uniform family of games that are polynomially bounded, the verifiers. So the first step runs in constant time, since our compression algorithm is just running on the description of this family, which is just some constant amount of bits. And then the second step with probability 1/2 runs the compress n+1th game, which by the guarantee of our compression theorem runs in polylog n time. And then with probability 1/2, it runs hn, which again is a polynomially bounded game. Therefore, this entire verifier is polynomially bounded. Okay, so this is the definition of the new family of games that we've produced using our compression. And now we're going to argue that the first game from this family has the supercompression properties that we require. Okay, our claim is that the quantum or commuting operator value of the first game of this new family that we defined is 1 if and only if every single member of the original family we wish to supercompress has a quantum or commuting operator value of 1. I put T here to illustrate that this proof works for both the quantum and commuting operator values. I've also over here put, for our convenience, again, a small description of the family of games and the guarantees that our compression result gives us so that we can more easily see the proof of this claim. So first, let's assume that every single game in our original family indeed does have a value that's 1. Then, we know that the nth game in this new family, by definition, is going to be equal to 1/2 plus 1/2 times the value of its compression. Since with probability 1/2, it plays the n+1 compressed game, and probability 1/2, it plays this game which has a value 1 by assumption. Now we use the first guarantee from our compression result to lower bound the value of the n+1 compressed game by the value of the n+1 game, and therefore lower bound the nth game's value by the n+1 game value in this way, by 3/4 plus 1/4 times the value of the n+1 game. Now we can repeat this process to lower bound the n+1 game by the n+2 game, and so on and so forth. And then by recursively doing this process, we can get the result that the first game in this family, or in fact any of the games, this is true for it, its value is lower bounded by 1 minus this following limit, which approaches 0. Therefore, from this we get that the first game in this family has a value that's 1. Perfect. On the other hand, if at least one of the original family games has a value that's less than 1, say for some k, hk for some k has a value that's less than 1, then by definition we know that the kth game in our new family also has a value less than 1, since it's just half times something, which is bounded by 1, the value of the compressed game, plus a half times the value of the kth original game, which we know is less than a half now. Therefore, from this we get that the value of the kth game of our new family is less than 1. But that immediately tells us that the value of the kth compressed game is less than 1 by the second guarantee of our compression theorem. Now, by definition, this also means that the k-1th game's value is less than 1, since with probability 1/2 it plays the compressed kth game. We can recursively enumerate this, keep doing this process, until we get the result that the first game in our family indeed has a value less than 1. So we've exactly shown what we wanted. We showed that this new family of games that with half probability plays its own compression, and with a half probability plays the original family of games, has a property that the first game in its family, that one game, has a value 1, if and only if every single game in the original family we wish to supercompress has a value 1. Now we can also argue about the entanglement requirement for this game. We can see that the amount of entanglement that's required to win the nth game in our family perfectly is clearly lower bounded by the amount of entanglement needed to win the n+1th compressed game, since in order to win this game perfectly, half the time we are playing the compressed game, so we must be able to also win this game perfectly, so the amount of entanglement for the former must at least be as large as the amount of entanglement for the latter. Now, we can also lower bound this entanglement requirement for the compressed game by using the third guarantee of our compression result to get the following expression. This is true for every n, and we can recursively lower bound each of these to obtain that the entanglement requirement for the first game, or in fact any of the games in the family, to win perfectly, is lower bounded by the maximum of the entanglement requirement for the nth game and n for every n. This is unbounded, therefore the entanglement requirement for the first game to be won perfectly is infinite. Namely, no finite dimensional strategy individually can perfectly win this game that our supercompression is giving us, even though maybe a supremum over these games can have a value that's 1. Namely, arbitrary better and better strategies, which are finite dimensional, but none that perfectly wins. Okay, so let's recap what we've done. We have used the compression theorem that we prove in this paper to map any uniform polynomial bounded family of games Hn to a single game G, so that that game has a quantum or commuting operator value 1 if and only if every single game in that original family had a value 1. This process we call supercompression. Furthermore, this game has a property that it has an infinite amount of entanglement requirement to be won perfectly. Namely, no finite dimensional strategy wins a game perfectly. Okay, so we've constructed this supercompression map algorithm. Now, we're going to show how almost immediately we can apply this supercompression to get the hardness results that I promised you at the beginning of the talk. So application. We'll show how we can reduce the non-halting problem now to the exact commuting operator and exact quantum value problems. Let's define a family of games to supercompress now. Let the family Hn be as such. The nth game's verifier runs a Turing machine, the Turing machine we want to decide non-halting for, on a given input for n steps. Then it automatically either rejects and makes the players lose with probability, so the players can win with probability 0, if in that n steps the Turing machine halted. Otherwise, it automatically accepts and the players win if it did not halt. Now, if our Turing machine never halts on the input x, then for every single n, this game Hn will automatically win, since it never halts in any n steps. Therefore, if our Turing machine on a given input x is non-halting, then every single game in this family has a value 1. But if it does halt, for example, after k steps, then hk plus 1, and every subsequent game will have a value that's 0, quantum or commuting operator, because the verifier does not actually play the game. So We've taken the problem of deciding if a Turing machine runs forever, the non-halting problem, and produced a family of games such that that is true if and only if every single game in this family has a value 1. Now here is a family that we can apply supercompression to. With supercompression, we can map this family of games to one single game such that it having a value 1 is equivalent to the above. And that's exactly what we want to do. We've reduced the non-halting problem to deciding the quantum or commuting operator value of a single game. Exactly. Now this is tight for the exact co-problem. Since there's a NPA hierarchy, which gives us a Coary algorithm to decide the exact co-problem. But for this problem of exact Q, this is not tight, and in the next few slides we will see a stronger reduction from universal halting. And let's also note that this immediately also gives an alternate proof of the non-closure of the set of quantum correlations, which was also originally proven by William Slofstra, since we have here produced a family of we've produced a single game that has a quantum value 1, if, for example, the original Turing machine was running forever. But we know from the guarantees of the supercompression result that this game, even though it has a quantum value 1, no individual finite dimensional strategy will be able to witness this, will be able to win it perfectly, even though the supremum does. Therefore, the set of quantum correlations is also not closed, is a result, is an immediate consequence of our supercompression theorem. Now, next application, we will show how we can combine the supercompression with the MIP star equals RE result to get the reduction from the universal halting problem to the exact quantum value problem. For a Turing machine and a given input x, we would like to make a game hx such that the quantum value of this game is 1 if the Turing machine halts on that given input. Otherwise, the value is bounded. This is exactly what we can get from the reduction from the halting problem to the approximate quantum problem that we get from the MIP star equals RE paper. Now we have a family of games, one game for each possible input, indexed by each possible input. Therefore, we apply supercompression, and we get a single game that has a quantum value 1, if and only if every single one of these games has a quantum value 1, which is true if and only if the Turing machine halts on every single input. Perfect. We've reduced the universal halting problem, therefore, to deciding the exact quantum value problem, which is what we wanted. This, in fact, is tight. I've, of course, been just giving high-level overviews of the actual arguments in the result. And one thing that might be concerning for you is that, okay, is this really a polynomially bounded family of games that we get from the halting to approximate Q reduction to then be able to apply the supercompression? And yes, this is the case. We do get a polynomially bounded family to then be able to apply the supercompression to. Okay, so let's recap. This is now the computability landscape of these four decision problems associated to quantum values of games. We've shown in our result that the universal halting problem is equivalent to the exact quantum value problem. What now remains is to resolve the problem about approximate commuting operator model.